Hi, I'm Zabback. I'm in a group with Timothy Brumfiel and Grell. Today I'll be presenting on our evaluation of our ME2110 designs. In ME2110, students are tasked with creating an autonomous machine to perform various basic tasks. We used various design tools to create 4 alternative designs, which we evaluated using 2 evaluation matrices. To begin the design process, we created a function tree, which is a tool that breaks competition tasks down into functions. We identified 6 main functions for the machine and broke those down into 14 subfunctions. We found that the most complicated function would be imprisoning Grindelwald, as this includes the most number of subfunctions. Next, we created the morph chart, which is a design tool that helps generate different design concepts for each of the 14 subfunctions in the function tree. This is the morph chart path for our first design concept. It uses a swinging arm powered by a pneumatic piston to smack the Dementor out of the home zone. Then it uses a scoop with a sorting track and gravity to ingress the gems and nifflers, sort them, and then drop them into the respective zones. Then it uses a scissor arm with an IR sensor mounted on it to detect when the barrier drops in the center, then a cannon to launch Grindelwald into the center, and finally a scissor arm to retract the machine. Here you can see a CAD model of our first design. This is the swinging arm that hits the Dementor out of the zone, the pneumatic cannon which launches Grindelwald into the center zone, and the scissor arm which brings the gem and niffler sorter to the center and sorts and collects the gems and nifflers. You can see the morph chart path for our second design concept. It uses a pneumatic piston and a sliding arm to reach the center, a spring launcher and a claw to grapple in the Dementor, a wedge mechanism and a sorting track, and gravity to collect, sort, and drop the gems. It does the same mechanism for the nifflers. For Grindelwald, it uses a scissor arm with an IR sensor mounted on it to move to the center, deposit Grindelwald, and egress. Finally, the entire machine uses a motor with scissor arms to egress the machine. Here's the CAD model for our second design alternative. Here's the piston, which pushes the sliding arms out to the center. Here's a sorting device, which ingresses the gems and nifflers and sorts them. Then we have the scissor arm with the preloaded tennis ball. It reaches out to the middle. Once this is deployed, detects the barrier drop with the IR sensor and deposits the tennis ball. Then we have a grappling hook powered by a piston which launches out to the dog bone, and then a motor which pulls the dog bone in. Here's the morph chart for our third design concept. It uses a set of swinging arms powered by a mousetrap to push a cart out to the center zone. Then when the cart is retracted by a motor that pulls the Dementor outside the home zone, we use a ramp to pick up the Dementor and sweep it back. Then we have a similar mechanism as the previous design to ingress the gems and nifflers and sort them. Then we have, again, a scissor arm that goes to the center, detects the barrier drop with a micro switch, deposits Grindelwald, and then egresses. Here's the CAD model for a third design alternative. It uses these 2 mouse traps to push these arms out to the center zone. Then this scooper would collect the dog bone in the center when this motor retracts the entire cart, pushing the dog bone back into the starting zone. Then this here ingresses the nifflers and sorts them. Then mounted on that is the scissor arm with the tennis ball device and the IR sensor, which would go out to the center, detect the barrier drop, and then deposit Grindelwald. Looking at the morph chart for our final design, we again have a pneumatic piston which is pushing out a cart to the center and using a scooping claw to pull back the Dementor into the starting zone when the cart deploys. Then we have again a mechanism with a wedge to ingress the gems and nifflers, sorts them with a track, and then drop them into the correct zone. We also have a scissor arm with an IR sensor mounted on it that detects when the barrier drops, deposits Grindelwald, and then retracts. You can see the CAD model for our final design. Again, it includes these sliding arms and a cart, which is pushed out to the middle by this piston. The system uses a scooper and ramp to ingress the gems and sorts them using this track. To deposit Grindelwald, we have this scissor arm, which is powered by a motor, reaches the center, and then this component lifts, dropping the tennis ball into the center when the arm is fully deployed. Finally, we have this dog bone scoop, which picks up the dog bone and pushes it into the starting zone. Of these mechanisms, only the cart deployment mechanism and the scooper mechanism have been tested. Preliminary results show that the cart mechanism works well, except that sometimes minor variations in the manufacturing of the arms can cause the cart to torque slightly to the left or right when the mechanism is deployed. Also, with the scooper, we found that it works well at sorting the gems, except when nifflers sometimes reach under the scooper, causing gems and nifflers to fail to ingress. Next, we begin our evaluation of the designs. To do this, we created a house of quality, which compares customer requirements to engineering requirements and generates a set of importance weights that we used in our evaluation matrix. From our house of quality, we found that the three most important engineering requirements were that the machine have an effective sorting device, that the machine be easy to set up and remove at the beginning of each round, and that the machine can accurately detect the location of the center. You can see our first level evaluation matrix, which compares our final design with our three other designs, with the final design as the benchmark, and using different criteria from the house of quality to compare each of the designs. From this, we found that the second design concept performed the best of the three design concepts, and the third one performed the worst, with the final design scoring higher than all three. You can see our level 2 evaluation matrix, which evaluates each of the design concepts using the criteria from the house of quality and their relative importance. We found again that the final design had the highest total score and beat all the other designs, confirming our final design as the best option. Many of these points came from the high reliability and simplicity of our first design compared to the other ones. Thank you. Any questions?